In last lecture, that was the first lecture of this chapter, we completed almost everything that is required in terms of theory, okay? And especially the concept of binding energy and binding energy per nucleon. That concept we have to understand very properly, okay? And that is what is going to help us solve such problems. And these are the type of problems that are actually asked in your exams, okay? So let's try to solve it, and I hope that it should not be difficult, okay? Because it is not difficult, okay? So let's start with this. Before we do that, let's refresh it one more time here. Binding energy. What is the binding energy? Okay, the general concept. Okay, this amazing thing happens when you bring in more than one nucleons together. Okay, two protons, two neutrons, one proton, one neutron. Okay, any number of nucleons together. When you bring them together to make one nucleus, to form one nucleus, okay, then the mass decreases. Okay, the mass decreases. The mass of the constituents, total mass of all the constituents taken together. Okay, and when they form nucleus, there is a mass difference. Okay, the mass of nucleus is always smaller, lower than the total mass of the constituents. That difference is known as mass defect, and the energy, the equivalent energy according to the Einstein's relation, that energy is known as binding energy. And if we divide binding energy by number of nucleons, that is the mass number, then we get what we know as binding energy per nucleon. Okay, and there is a very special significance of binding energy per nucleon. Higher the value, higher is stability. The more binding energy per nucleon I have, more stable that nucleus is going to be. Okay, now using that concept, let's start the first question itself. Okay, I have this three nuclei, okay, A, B and C, okay, their binding energies are given, the atomic, the mass numbers are given, okay. So let's, we have to find the stability, okay, the order of stability. So here I have A, okay, A is mass number, okay, it's here. So this, here I have mass number, it is 20, it is 5, it is 10 here, and then this is binding energy, okay, in the mega electron volt, it is 170, the same thing that is written here, and 90 and 120 here. Now this is binding energy per nucleon, okay. Okay, how do I do it? I will just divide it, 170 over 20, it becomes 8.5 mega electron volt per nucleon. Okay, this will be 90 over 5, this becomes 18, and 120 over 10, this becomes 12. Now higher the binding energy, okay, binding energy per nucleon, okay, it will be B is more than C is more than A, okay, then stability will have same order, okay, stability, okay, same order, okay, B, C and A. So out of these three, B is going to be the most stable. You see, look at, it does not have the highest binding energy. This has the highest binding energy, you see, but binding energy per nucleon is highest for this. So not the binding energy, but binding energy per nucleon is going to decide the stability of nucleus. Okay, so this has a highest value for binding energy per nucleon. This is going to be the most stable, and even though the binding energy is highest here, but binding energy per nucleon is lowest. Okay, so it is going to have the lowest stability. Understand that? Understood? Okay. Now, okay, next one. Binding energy of alpha particles. Binding energy of alpha particle. Okay. What is binding energy of alpha particle? Alpha particle. What is alpha particle? Two protons and two neutrons. Helium nucleus. Helium nucleus is alpha particle. Okay. So it's like this. I have one proton here, one proton, one neutron and one neutron. Okay, they are separate. Let me write it like this. One proton here, proton, neutron, neutron. Okay. I have these four separate protons and neutrons. They are separate. Okay. I am collecting all of them together and making a nucleus. Okay. Now when I make the nucleus, okay, all of them are going to be inside this nucleus here. Inside this nucleus. So proton, proton, neutron, neutron. It's like this. I make a nucleus. Okay. And then I will have these two electrons also. Okay. One electron here and one electron here. Electron. This is my helium atom. This is my helium atom. Okay. This mass is given. Mass of helium atom. Okay. Helium atom is electron, proton, neutron. Okay, everything is helium atom. It is 4.003 U. Okay, 4.003 U. Okay, understand? Now this will be equal to mass of helium nucleus plus mass of two electrons. Okay. Now what is mass defect? Okay, what is mass here? Mass here is equal to 2 times of mass of proton plus 2 times of mass of neutron. Okay. It is given here. Okay, so 2 times of 1.007 plus 1.008. Okay. This becomes 2 times of 2.015. Okay. This becomes 4.030. 030. What is this? This is the mass of these four constituents. These four constituents. Okay. What is the mass defect? What is the mass defect? Okay. Okay, no, I think I should write electrons also. Plus electrons. Plus 2 times of mass of electron. Okay. Plus 2 times of mass of electron. Okay, let me write it this way. I think this will be more suitable. So this is going to be equal to 2 times of 2.015 plus 2 times of mass of electron. This is 4.030 U plus 2 times of mass of electron. Okay, now this should have been the mass of this helium atom, but it is not. It is different. It is different. Okay, then what is the mass defect? Okay, what is the mass defect? Mass defect is equal to 4.030 U plus 2 times of mass of electron, okay, minus 4.003 U. Okay. Mass of electron is not given, okay, in this problem. In this problem, mass of electron is not given. Okay, so what we have, okay, so either if you know this, you can use the value. Okay, but if generally these values are not expected to be remembered, if some problem is asked, they will provide you that value. Now, if the value is not provided, then you are expected to solve it without using that value. Okay, that means even though I know mass of electron, but I am not expected to use that value because it is not given here. It is not given here. Okay, in that case I will ignore it. I will ignore it. Okay, then this will be equal to 0.027 U. This is mass defect delta M. Okay, then binding energy is delta M times C square. Okay, either I can use this or I can write 1 U is equivalent to 931.5 mega electron volt. Okay, so binding energy 0. Okay, so binding energy is equal to 0.027 times 931.5 mega electron volt. Try to make sense out of this. Okay, let me see if you are able to see it clearly. Okay. Okay. Do you understand this? Either you make this calculation. This will be 0.027 into 1.66 10 minus 27. Okay, this becomes kilogram into 3 into 10 power 8 square. This becomes joule. Okay, and then you convert this into electron volt and then mega electron volt. Okay, or million electron volt. You will get the same answer. You are going to get exactly same answer. Okay, but this type of calculation is not required. It is not expected. What is expected is you are able to calculate in this manner here. Okay, mass energy equivalent 1 U. This is the mass defect. Okay, now mass defect of 1 U mass is equivalent to 931.5 mega electron volt energy. Okay, so what will be the energy equivalent to this mass? I can make this calculation directly. I do not have to write this whole thing here. Okay, we remember this thing. This is a standard relation that I have to remember. I have to memorize it. Okay, so using this I can make my calculation directly. So this is the binding energy of helium nucleus of alpha particle. Helium nucleus. What it means that if I have an alpha particle, okay, then I need to supply this much energy to break it apart into all the individual components. Okay, you understand this? Okay, this is binding energy. Here we are ignoring the mass of electron. Okay, mass of electron. And anyway, when I write this delta M, okay, it is the difference in mass of nucleus from its constituents. Okay, from its constituents. I can solve the same problem in a different manner. Okay, I can solve it in a different manner also. Okay, let's see what is the other manner. I hope that you follow it clearly, okay, without any confusion. When we say mass defect, that means the difference in mass of the nucleus from its constituents. Okay, do you understand this? Okay, now this is helium atom, mass of helium atom. I will write like this: mass of helium atom is 4.003 U. It is given. Okay, so ignoring the masses of electrons, okay, mass of helium nucleus is approximately 4.003 U. Okay, I can think the same problem in this way also. Okay, and in that case I will not consider electrons here. Okay, then there is no need of considering electrons. Do you understand this? Okay. So it is like 4.030 U minus 4.003 U. That's it. Then I will not consider the mass of electrons here. Okay, because here I have already ignored. Okay. Anyway, when I say mass defect, then I'm concerned only with the difference in the mass of this nucleus, only this nucleus, okay, from its constituents. Okay, okay. Let's see more problem. Then you will understand. I'm sure. Okay. Keep it simple. Let's try to keep it simple as we can. Okay. But there is a limit to how much a given thing can be simplified. Sometimes oversimplification also kills the essence of that thing. Now, here, binding energy for nucleons of this calcium nucleus, okay? Calcium nucleus is given, okay? So I have this 20 protons plus 20 neutrons, okay? They make this nucleus, okay? 20p plus 20n, and then there will be electrons. Okay, there will be electrons. Okay, many electrons, 20 electrons. Okay, so here I have mass of calcium atom. It is given, okay, 40.01 U. Okay, that means 20 times mass of electron. Okay, so 20 mass of electron plus 20 times mass of proton plus 20 times mass of neutron, okay, is equal to 40.01 U. Okay, this is given. This is mass of calcium atom. Okay, now, okay, calcium atom. Now, hydrogen atom, neutron, these two are given. How do I make use of this? Okay, so here I will have plus 20 electron. Okay, what I want to find? I want to find binding energy. For that, I need to find what? I need to find the mass defect. Okay. How do I find mass defect? This mass is mass defect. Mass defect delta M is equal to. Okay, let's make use of that relation that we discussed in the previous lecture. It is equal to Z times of mass of electron plus Z times of mass of proton plus N times of mass of neutron over mass of that atom, mass defect of an atom X. Okay, now here the mass of electrons get subtracted. Okay, in this mass, the mass of electron is also included. Okay, so when I subtract it, the mass of electrons get subtracted. Okay, so what I will be left with will be the difference in mass of nucleus from its constituents. Okay, so this will become 20 protons plus 20 neutrons separate masses. Okay, and here I will have 20 protons, 20 neutrons taken together plus 20 electrons. Now these 20 electrons here are going to be cancelled by 20 electrons here. It gets subtracted. Now this I can write as but in this problem, the mass of electron is not given. Okay, so either I ignore it, okay, or I make some other rearrangement. Mass of proton is also not given. This is not given. You say this is given, this is given, this is given, but these two are not given. But instead of these two, okay, you see, if they are not given, then I can ignore this, but I cannot ignore this. Okay. Now, if these two are not given, then in place of these two, something else is given. What is that? That is mass of hydrogen atom. Okay. So we are going to make use of this. Okay. This will be equal to Z times mass of hydrogen. Electron plus proton, one electron plus one proton. Okay. They make a hydrogen atom. Plus n times of mass of neutron minus mass of X. Okay. Now this will be 20 times mass of hydrogen atom. It is 1.0075 plus 20. Okay, here Z is 20, okay, A is 40, N is 40 minus 20 is 20. All three are this for 20. 20, okay, 20 times 1.008. It is already given here. Okay, minus the mass of calcium atom is given. Okay, it is 40.01. That's how we do it. Okay. So this becomes 20 times, this becomes 1 and 1, 2.008, so 8 and 7, 155 minus 40.01. Okay, so here it becomes 40.3, 310, okay, minus 40.01. This becomes 0.3 U. This is delta N. 0.3 U. Okay. So binding energy will be equal to 0.3 times 931.5 mega electron volt. Okay. This will be 45 here. Okay. 45 and 9. Okay, 4, 5, 9 and 27. Okay, so 279.45. This becomes million electron volt. What is this? This is binding energy of calcium. Calcium what? Calcium nucleus. We are studying nucleus. Okay, it is not the binding energy of atom. This is the binding energy of calcium nucleus. Understand this? That's why we are making all this type of calculations. Okay, that's why we discussed so much about it, so that you are not confused. Here we are just concerned this way. When I write mass defect, this mass defect is only the mass difference between the nucleus, not the atoms. But we can make our calculation using the mass of atom also. Mass of atom also. Okay. Because the mass of electrons are getting subtracted. Okay, so what I am left with will be mass of proton plus neutrons on one side and mass of the nucleus on the other side. Okay, I hope that you are not getting confused. Okay, so this is binding energy. Okay, what will be binding energy per nucleon? This is binding energy. Okay, so binding energy per nucleon is equal to 279.45 over 40. Okay, so this is approximately 7. Okay, 7 mega electron volt. Approximate answer. Approximately it is going to be 7. Okay, mega electron volt per nucleon. Binding energy per nucleon. Okay, now the next one. Now, next one is something that requires some thought. What is the meaning of binding energy? Now, can you answer it in a single attempt? Can you answer this question in a single attempt? In a single attempt, can you do that? Can you do this? Can you answer this in a single attempt? What is the meaning of binding energy? Okay, I have some nucleus. Okay, protons are packed together. Okay, they are packed together. I want to break it into separate protons. Okay, it's like this. I want to break it into separate constituents. Okay, far separated. Okay, whatever energy is required, that is binding energy. Now, when the constituents are far separated, in that case, its energy here, potential energy is going to be zero. There is no interaction, and when there is no interaction, there is no potential energy. Okay, it is going to be zero. Now, so what will be energy here? If the binding energy is 150 mega electron volt, that means this much energy is required. So if I supply this much energy, then all the particles will be separated. Then the energy of system becomes zero. If I provide this much energy, then energy of system becomes zero. Okay, so this is my initial energy, and this is my final energy. I am providing it binding energy. Okay, so it's like this: U initial plus binding energy is equal to U final. Okay, U initial plus 150 is equal to 0. U initial is minus 150 mega electron volt. Okay, that means this is the nucleus. Okay, this is the nucleus. The energy here is minus 150 mega electron volt. Okay, and then if I want to separate it, energy here is 0 at infinity. At infinity means they are far separated. Okay, energy is 0. So I need to provide 150 electron volt, 150 mega electron volt. Okay, this becomes the binding energy. This much energy I need to provide. Now what will happen? Now the question is, what is the new binding energy if 10 mega electron volt energy is absorbed? Okay, do you understand this? That means if I supply some energy, if I supply it 150 mega electron volt, it is going to be broken apart. I am not supplying that much energy. I am supplying only 10 mega electron volt. Okay, so from this state, okay, the nucleus is going to be in this state. If I am supplying it 10 mega electron volt, then its energy will become minus 140 mega electron volt. Okay, then what will be its new binding energy? It will be 140 mega electron volt. Okay, so from 150 it will become 140 mega electron volt. Okay, now if the nucleus releases 10 mega electron volt energy. Now if it releases some energy, its energy is going to decrease further. Mega electron volt. Okay, it is releasing 10 mega electron volt. Okay, now my nucleus is in this state here. Okay. And then if I want to break it, I will have to provide this much energy here. This much from here to here. Okay, this becomes the new binding energy. This becomes 160 mega electron volt. Okay. Okay, that's how we solve it. I hope that you were able to see it clearly. Like, is it focused well? Let me check. Okay, I hope that it's fine now. Or is it not? Maybe it's not. Now? Okay. The next question, a new term. What is the new term here? Q value. Q value. Q value of following reactions. Now, what are these reactions? These are not the normal chemical reactions. Okay, they are known as nuclear reactions. Okay, nuclear reactions. Nuclear reactions. Okay. Nucleus changes. Nuclei undergo change. Okay. In chemical reactions, the nucleus does not change. Okay. So if I am let's say calcium reacts with some acid, or okay, one compound reacts with some other compound, then whatever are the atoms in the reactants, I am going to get exactly same atoms in the product also. The nucleus does not change. Molecules change. The structure changes. Okay. But the atom, the nucleus remains the same. It does not change. Those are chemical reactions. In nuclear reactions, the nucleus itself changes. Okay. See here. These are the reactants. These two nucleus are reacting. Okay. These two nucleus, helium, this is the nucleus of hydrogen, and this is the nucleus of hydrogen. Okay. Normal hydrogen, this is atomic number is same, mass number is different. They are isotopes. Okay. Now when these two react, they are making a nucleus of helium. You see, the nucleus itself has changed. Plus one neutron is emitted. Here, two hydrogen nucleus, then they are making one helium nucleus, and one neutron is emitted. Okay. Lithium nucleus changes into, okay, so here this is lithium nucleus. A nitrogen, it absorbs a nitrogen, or we can say that a nitrogen reacts with, not nitrogen, this is neutron. A neutron reacts with lithium nucleus, not the atom, nucleus. And then we get two different nuclei. We get hydrogen 3 and helium 4, nucleus. They are known as nuclear reactions. Okay, nuclei undergo change. Okay, energy absorbed or released is called Q value of reaction. Okay. So in each of these processes, energy is either going to be absorbed or it is going to be released. Okay. Now two types. We have two types of nuclear, two basic types. Okay. The first one is known as fusion, and the second one is known as fission. Okay. Now, what is the meaning of fusion? Okay, two nuclei. Okay, two nuclei. Let's say A plus B. Okay, they fuse together. They become C. Two nuclei fusing together to become one nuclei. One neutron is emitted. Two nuclei fusing to become one nuclei, one neutron is ejected. Okay, here, what is this reaction? Okay, this is known as fusion reaction. Okay, now what is fission? Fission. Now this is of two types. One is natural fission. Natural is like this: A changes into B plus C plus R. Okay. So one nucleus, it disintegrates into two or more than two nuclei. It is known as natural fission. Radioactivity is spontaneous fission. Radioactivity is known as, is one example of natural fission. Okay, a nucleus automatically on its own, spontaneously undergoes this change. It is known as natural. Now artificial. Okay, I have this nucleus. I bombard it with nitrogen, neutron. Okay, then it changes into some B plus C and all that. Okay, like what's happening here. Okay, I can also bombard it with alpha particles. Okay, let's say this is A plus some alpha particle here. It is B plus C plus D plus all that. Okay, and in each case, some energy is either absorbed or some energy is released. Okay, so that amount is known as Q value. Q value. Okay, now how do I calculate it? Q value is equal to delta M and C square. Delta M is mass defect. Okay. Delta M is mass defect. Mass defect. So if I have this reaction, A plus B is equal to C plus D. Okay. This is mass of reactants. Okay, let me write it like this. These two are reacting and these two are products. This becomes mass of product. Mass of reactant, mass of product. There is going to be some mass difference. Okay. When I'm saying mass defect, that means the difference in mass of nucleus, not the atoms. Okay? You understand this? Difference in mass of nucleus. Nucleus of the reactants and nucleus of the product. Okay, nucleus only. Not the atom. But we can do our calculation with the atomic masses also, because the number of neutrons are going to be same on both sides. Do you understand this? We will do these problems and then you will understand. Okay. So now delta M will be going to be equal to mass of reactant minus mass of product. Okay. Now if mass of reactant is more than mass of product, then delta M is positive. Then Q is positive. It will be exothermic. Mass of reactant nuclei is more than mass of the product nuclei. Okay. In that case, Q value will be positive. Energy will be released. It becomes exothermic. Okay. And if mass of reactant is less than mass of product, okay, in that case delta M is negative. Okay. Q is negative. Q is negative. That means it is endothermic. Endothermic. Okay. Okay, let's do this problem. Then they will understand. It's not so difficult. Okay. This theory might appear little difficult, but once we do few problems, it becomes very simple. Okay. Do not worry about the masses, whether you should use the mass of nucleus or mass of atom. You see, even if you use mass of atom on both sides, because you see, the number of electrons are going to be conserved. Number of protons are going to be conserved. Okay? Neutrons are going to be conserved in any reaction. Okay? So, when we say mass defect, it is the difference in masses of nucleus. Okay. But we can also make our calculation by taking the mass of atoms also, because the number of electrons are same on both sides, so they are going to be balanced. Okay, so generally we are never really required to bother about it. So whatever data is given, we directly use that data to get our answer. Okay, let's look at a few problems here. Okay, let's look at a few problems. We are going to use this data. Okay. Now this is hydrogen 1 plus hydrogen 1 is equal to helium 2 plus 1 neutron is emitted. Okay, that's it. This is my reaction. I want to find the Q value. Okay, what I will do? I will look at the mass of reactants. Okay, mass of reactant is equal to mass of reactant. Hydrogen, this is given here. So it is 1.0075 plus hydrogen 3. This is hydrogen 3. 3.016. Okay. Now mass of product. Helium 2,3 here. Helium, where is helium 2,3? Okay, here. This is helium 3. Okay. So 3.016. This is 3.016 plus mass of 1 neutron. It is given here. Okay. 1.008. This will be equal to 3.024 U. This is mass of product. What is mass of reactant? This becomes 4.0. This is 3.016. Okay. So 4.0235. 235. What has happened? Mass of reactants is less than mass of product. Mass of product has increased. Okay. What will be delta M? There is mass defect. Mass of reactant minus mass of product. Okay. So 4.0235 minus 3.024. This is 0.000005. Does that make sense? 0.0005 U minus of this. So what will be Q value? Q will be minus of 0.0005 and 931.5 mega electron volt. I am getting a negative Q value. Okay, that means this process is exothermic, endothermic. Okay. That means it is not spontaneous. This process will not happen on its own. Okay. So if I want this reaction to take place, I will have to supply energy. That means I will have to give them some energy. I will have to fuse them forcibly. Okay. I will have to bombard them towards each other by supplying them kinetic energy. Only then this reaction will happen. This is an endothermic reaction. Energy is required for this reaction. Okay, so endothermic reactions are not spontaneous. Exothermic reactions are spontaneous. Okay, let's see if this is exothermic. Okay, let's find out. Whichever is exothermic, it becomes spontaneous. Now the second one. Okay. Okay, second one. What is delta M? Mass of reactant minus mass of product. Okay. Okay, these masses, they are for nucleus or for atom. Okay, so generally we are not really bothered. Okay, even if I take the masses of atom on both sides, I am going to get the required mass defect. I am emphasizing this point again and again because it is the most confusing point in such type of calculations. Okay, so that's why I am doing it several times. Okay, in problem sheet also I am going to give you some problems where you may have some confusion. Okay, and you have to come out of this confusion. It's very important. Mass of reactant. These are the reactants. Okay, so two atoms of two nucleus of hydrogen 2. This is hydrogen 2. Okay, it is 2 times 2.014 minus product. What is the product? This is product. Okay, helium 3. This is helium 3 here. Okay, minus 3.016 plus 1.008 mass of neutron. Okay, this is 4.028 minus, this becomes 4.024. Okay, we are getting a positive answer here, plus 0.004. Okay, now so what is Q value? Plus 0.004 and 931.5 mega electron volt. Okay, so 3 decimals here, it becomes 604, 3.7260. Okay, mega electron volt. It's a positive answer, that means it is exothermic. It will be spontaneous. This is exothermic. Okay, it will be spontaneous. Masses of reactant is more than mass of product. That means some mass has been converted into energy. So that much energy, this much energy will come out. This is Q value. That means this much energy will be released if this reaction happens. Okay. Now let's look at this last one here. Okay. Now the last one. Last one is lithium 6 plus a neutron. I get helium 3 plus hydrogen 3 plus helium 4 plus some Q. Okay. Now delta M is equal to mass of reactant. Okay, reacting nuclei. Lithium 6 is given 6.015 plus 1.008. This is for neutron here, minus hydrogen 3. This is hydrogen 3. Okay, 3.016 plus helium 4. Okay, 4.0026. Okay, now so we have this answer. So 7.023 minus 7.001, so 4.0026. So 7.010186, like this. Okay. So that's it. This is positive. It is positive. So Q is positive. Exothermic. That's how we make our calculations. Okay. You understand? Okay. Let's do few more problems. Okay. Let's do, because all these values are given. Okay. So let's do one more problem of this type. Let me write few more problems. Let me write one more, okay? Question. How much energy is required to remove a neutron from helium nucleus? From helium nucleus. So from helium nucleus, I want to remove one electron. Okay, that means I have this normal helium nucleus, He4. Now from this, I want to remove a neutron. Then this nucleus will change. It cannot remain this. It will change into this. Okay. What do you think? How much energy will be required? Okay. Okay, and let's okay, so I hope that you should be able to do all of this. Okay, so it's like this. Okay, so you simply write delta n will be equal to helium 4, it is this here, 4.0026 minus, these are the product, so helium 3.016, okay, plus 1.008, okay, so 4.0026 minus 4.024. That's it. What do I have? Do I have a positive answer or a negative answer? Positive or negative? This is going to be, this is the masses of reactant. This is the reactant nucleus. Okay. Mass here is less than this mass. Okay. Mass has increased. In a reaction, mass has increased. Okay, that means we are supplying some energy. Okay. This is going to be negative. This is going to be negative. Okay. That means Q is negative. It is endothermic. This is endothermic. It is not spontaneous. Okay, it is not spontaneous. Okay. So it will not happen on its own. Okay, so that's it about it. Let's do one last problem. Okay, we have a different type of reaction here. Okay. Okay, note down this problem. This will be the last problem. A nucleus of mass number A is at rest. Okay, what is its recoil speed if it emits an alpha particle with speed v. Okay, let's do this only with speed v. Last problem here with speed v. A simple problem, last problem. The chances are we actually have done this problem, okay? Not this year, but last year, in last year's course. Okay, try to solve it. Let's see if you are able to recollect all the concepts from the previous year. Okay, so I have this nucleus. Okay, so there are many protons, many neutrons. Protons, neutron. Okay, many protons, many neutrons. Its mass number is A. That means number of protons plus number of neutrons. It is A. It is given, already given. Okay. It emits an alpha particle. It is at rest. It's like a gun is fired. A gun is at rest. A loaded gun, a gun loaded with bullet is at rest. Gun is fired. Gun recoils. Okay, so we have to find its recoil speed. This alpha particle goes out with speed v. Alpha particle. Okay. So solve it. I think you should be able to solve it. This is also a type of nuclear reaction. Okay, so from a nucleus, it undergoes some decay process. We are going to study decay process when we start radioactivity. Okay, maybe after the next lecture. Okay, so this is also a nuclear reaction. Now, so this is at rest. This is mass number A. Okay, it is at rest here. It is at rest. Okay, initial momentum is 0. Okay, so finally also it should be 0. Now this changes into one alpha particle. This is my alpha particle, and this is my remaining nucleus. It becomes A minus 4. A minus 4. Okay, so this has certain velocity. Let's say v naught. Let me write it as v naught. Speed v naught. Then it will recoil in this this direction, in opposite direction. Okay, such that final momentum is also 0. Okay, so I will simply write like this: a minus 4 times v. Okay, why I am writing it? I need to write momentum, I need to write mass. Okay, so I am doing this assumption: mass of proton is mass of neutron is equal to m. Okay, so this mass here will be a minus 4 times m. This becomes mass times speed is equal to, both momentum should be equal and opposite. This becomes 4. Okay, this is 2 proton plus 2 neutron. It is alpha particle. Okay, is equal to 4 times of mass and v naught. Okay, we have this answer. V will be 4 over a minus 4 and v. Okay, in problem sheet you are going to find a few more problems of the same type. Okay, I just gave you one method of solving it. In problem sheet you are going to find a single problem with certain different parameters. Okay, in terms of kinetic energy we have to find alpha particles comes out with certain kinetic energy. What will be kinetic energy of the remaining nucleus? Okay, such type of calculations problems you are going to find. Okay, in problem sheet. Okay, so let's conclude this lecture here.